afternoon, everyone. We're Team 9, and our project is WOD, the weightlifting robot. My name is Leandria, and with me I have Juan, Cardona, and Murton. We're representing our faculty advisor, Dr. Tosunoglu, and FIU mechanical department. So for today, we'll give you our brief problem statement, which will include our description of our project, some motivation, a little bit of literature survey. Then we're going to go into some related standards, our challenges, as well as our design, global design, and how we constructed our project. Alongside that, we'll give you some future endeavors as well. Now to continue on with the project description, WOD is titled WOD because it's called Corrective Workout of the Day, kind of mimicking the CrossFit platform. Now, the project description, the base of this project was to encourage the idea of strength training in its uprise of importance. We're doing that by incorporating the fundamentals of lifting, which is knowledge, technique, and form. In doing this, we've seen a lack of expertise around different gym settings. So our motivation was, for one, artificial intelligence and humanoid robots. Two, the lack of expertise that I just mentioned. Going to the gym, you see a lot of even beginner and advanced lifters that do a lot of the workouts wrong, or they do it with incorrect form. Alongside that, our goals is not only to educate and elevate, but also to inspire others to pursue the art of weightlifting in its proper form. So to continue on the literature survey, here's Murton.
So just a brief literature survey review. Most people think, or a lot of people think, that robots are a relatively new thing, but they're actually over a century, a millennium old, dating back to the ancient Greeks, the Romans, the Egyptians, and they all made minor attempts at creating their own robots. Most of them were pulley systems, mechanical systems, either powered by gravity or water. But you fast forward about 1,000 years, and you get the invention of the robotic arm, and this really takes robotics to the next level. It's sort of the industrial revolution for robotics. And nowadays, the robotic arm is everywhere used in production lines, and we've advanced from that. Now we have a rover on Mars. But the newest thing as far as robotics goes, the sort of fad, if you want to call it, is humanoid robots. The three of us at our time here at FIU have done quite a bit of research with humanoid robots, so this is a project that felt right for us. Here's a picture of Robonaut, the R5, kind of an inspiration for us. Now I'm going to pass over to Juan, which is a little bit more on the project.
So as you can see, robots have advanced a lot through the years, and with time, they just keep getting better and better. With that, growing the opportunity for pretty much anyone to be able to build a robot. And we feel like there's two options to go about doing this. The first option would be to just start from scratch, which will be a good idea if you have a lot of time, because then you'll have to create your own design, manufacture it, buy all the different motors and electronics that you need to assemble it, and then program it to do what you need it to do. But if you don't have the time, we feel like you can use the second option that we think which is an open source humanoid robot, like the Flagler project, which is a project that a group of engineers put together, in which they created different designs of robots and made it available for pretty much anyone to go into the website and download them so that you can modify them to your own need. So basically, you download parts, and with a program like SolidWorks, you modify the parts as you need to, and you 3D print them. After you 3D print them, you order the electronics and wires, you put it together, assemble it, and program it. Like that, saving some time on manufacturing. So like I said, with robots comes programming, which is a whole bunch of lines of computer code that are language free to solve a problem. In our case, we have a problem which is that some people don't know how to lift weights properly. So as humans, we create a solution, we create a plan. In this case, it's WOD. WOD is we're gonna write a program. WOD is gonna follow that program. It's gonna do the program and reach a goal, which is to teach people how to lift weights properly.
So programming was actually a huge part of our project, and I don't mean like sitting down on a computer and typing days of code. What I mean is we took into our design consideration the program very heavily. There are three things that we wanted to do. The first was we wanted a code that worked with the motors for obvious reasons. The second was we wanted a language that made sense for this project. If all languages were the same, there would be no need for different types of codes. And the third, we wanted a language that we were at least familiar with, and Python met all three of those requirements. Now, after going through several different types of Python-based codes, we ended up with Jupyter, which is Python-based. It's a pretty simple code base working with motors. Alone, it's not a super sophisticated program, but when you pair it with VREP, which is a virtual simulation, really cool things happen. So because, like Juan said with the open source, we had a design before we ever started to design. We test all our programming on Jupyter, and in conjunction with VREP, we could test all our simulations. So we did all our programming actually ever before we did any design alterations, before we ordered any part, before we ordered any motor, and through VREP we actually made several changes to our design. Another thing we had to consider as far as our design was standards. Now, because our prototype is quite small, there weren't really any standards to apply to it. But CWOD is more than just an initial prototype. It's an idea of what it can become. And there are a couple standards that relate to it. The idea is that one day CWOD will be in high schools across the country, across the world, in gyms across the world. And to do that, you have to produce at a mass rate, and there are standards that relate to that. Also, this last one right here is a standard for vocabulary. One of the things that we wanted to do in our final design was speech receptors, and that goes into our global design. We wanted to have it multilingual. We also wanted to have multi-units, English and metric. With weightlifting, you have to know both. It doesn't make sense making a robot that teaches you how to weightlift if it can't convert between the two. One thing that we did as far as global design for our prototype was we printed in PLA, which is a bio-friendly plastic, as opposed to ABS, which is toxic to the environment.
So when we decided to do a human and robot to teach you how to weightlift properly, we had to go through different designs, trying to find the one that fit most of the qualities that we were looking for in a robot. The qualities that we were looking for was, one, to be an open source, because we wanted to save time in manufacturing, given the time frame that we have for the project in the past. And the other one was to have 20 or more joints, so that it can have more human-like features. We wanted it to be big in size, have feedback through audio and screen, and be cost efficient. So here you can see, go back there. Here you can see alternative 1, which was an open source human robot that was very small dimensions inside and didn't have a lot of human-like features. So we decided not to go with this design. So alternative 2 had more than 20 joints, which was ideal. It was an open source human robot, but again, it was small in size and it didn't have feedback through audio or screen, so we didn't feel like this was the one we were going to use. So for senior 1, this was actually the design that we chose. This is an open source human robot from the Puppy project. It has 33 inches in height, which is pretty big, and it has more than 20 joints. And but it wasn't cost efficient. We needed like about $7,000 to $8,000 to do all the 3D printing and get our motors. So go to the next one. So after we presented our project last semester, we had some feedback from the board, and one of the questions that they raised was how we were going to balance the robots that wouldn't fall while lifting weights. So we took that into consideration, and we thought that our first option was too complex, so we decided to shrink it a bit and just make it a base instead of the legs, create a torso on a robot. So, but with that final design, we came across some challenges. The first one being that we couldn't get all the funds that we needed, so we had to cut down on the motors that we were using. So to do that, we had to use the knowledge that we have learned here in school with SolidWorks and modify some of the parts to be able to get rid of the motors that were here in the torso area. And with that, we had some problems with 3D printing because the new parts that we created were not 3D printable because the machines were too small. So we had to play with the parts until we finally got a design that was 3D printable.
Alright, so now with the final design, as you guys will see here, this is our final design. Now all of these designs have the same parts when it comes to the torso and the limbs and what we're looking for, as you guys can see. So the torso has the base, the chest, the spine, as well as the motors that are in the chest. With the torso, you have the shoulders, the arm connector, and the forearms as the main parts, and then all the materials are printed in PLA, as Brian mentioned. So here's all the components after alteration. As you can see, we changed the head so it can have CWOD can have our identity that we wanted. We also changed the hands to end effectors so it can just hold the object that we have in it, which is a dumbbell. And we changed the chest drastically because we wanted CWOD to have our own look. And then for the base, we changed that as well because we didn't need the motors that were in the torso, so we changed that base completely. So here's a MX28 motors. We have 6 of these motors. They're very powerful motors. Now these motors, as you can tell, these dimensions fit within our project. And then one thing that we want to point out, we teamed up with one of the doctoral students, and we were trying to find a more cost-efficient efficient motors. With those motors, it came different dimensions, but also it has less torque, less speed, and a few other specifications that we needed to have for our robot. So we stuck with the motors that came with it, and we found a better funding option. So here's a cost analysis of our project. As we said, the 3D printed for 60 hours is $10 an hour, so they came up with $600. On the labor, we accumulated after all the hours we put into it, about 150 hours. If we were to charge at $25 an hour, it would be a total of $37.50, but I'm not included because it's our project, it's no cost. The motors were the most expensive. It was $13.58 because each motor was about $200 something. And then we had to buy a bearing set that was outside of the motors because it didn't come within a pack. So how do we assemble CWOD? So CWOD was easy to assemble because the parts are connected through the motors. So what we had to do first was, after the parts were printed, we cleaned the parts, as you'll see in the next slide. But we cleaned the parts because they had a lot of debris. We used also what we learned in Professor Zaccarelli's manufacturing class. We utilized those aspects to fix this project. After that, we had to assemble the motors. After we assembled these motors, we had to calibrate them using RoboPlus through Dynamix. So RoboPlus is pretty much a platform that you use to call the motors a certain name, give them certain IDs, so that when you're doing the programming, you can connect to it. And once we did that, we had to finish the assembly and test the program. So as you can see right here, this is the part after it was printed. It had a lot of debris. We had to sand it, get all the debris off. And then this is one of the basic assemblies, which is the motor to the arm connector that you can see here. And then here's a part of one of the arms. So how we tested it. Now, as he mentioned, VREP was one of the simulations. So what we did was we used the Jupyter programming. Now they have certain libraries called PyPy. PyPy has basic programs that you can see, even open source. They give you certain lines of code that you can use as a base. Now we use it as a base, but as I said, we have to call the motors a certain name, which is the most important part. In order to program these motors so it could read through Jupyter to VREP was many of the hours that we spent in labs and trying to figure out how to do it. Once we got that, we were able to use the certain lifts that will correlate with our programming and having just a torso, like the bicep curl, as you will see in our simulation, the frontal raise, the lateral raise, and the overhead press. Now, we know that this robot has very, very minimal load, so the testing that we were doing here is just to let you guys know we still understand for our future of the project, we have to consider these testing evaluations. So we just put a force of 1 Newton on the wrist, and what that is simulating is if you're holding a weight, or any type of weight, majority of that force is going to be within your wrist. If you guys ever done any weightlifting, go to the gym, you're holding the dumbbell, it's on that wrist. So we went through many load cycles, and you won't see many changes. It's just we wanted to do it so you all know what we're doing, the engineering aspect of it. Now, one of the most important tests that I found was very useful. Using work from one of the professors that we went to here, we used the shoulder as a fixed end. We used that, and then treated it like a cantilever beam, and we put the force at the wrist. The reason why we did that is because just as I told you all, if you're holding a dumbbell, that's how you would simulate where the stress is distributed. So here's a simulation. Right here, this robot's doing a bicep curl, and right here, an overhead press. Now, this is a VREP simulation. But now what we're going to give you, and which we can have if you guys want to see the actual robot doing it, a video of VREP doing it, the actual robot doing it. So that's the bicep curl. When the bicep curl is running, you're starting at a fixed head, you're going 90 degrees and back down into a tricep pullback. It should go to a certain angle and then back down. And then from there, it'll translate into a lateral raise. If you guys know the lateral raise, you go to shoulder raise and back down. There's the lateral raise after this raise. So CWOD, it was a very ambitious project, as we all know, but this is just phase 1 of many phases of this project. As you can say, for 1, it's a torso, we want the full body. 2, it doesn't have the visual receptors as we wanted, but we will get that as well. And as well as speakers for audio feedback as well. So we're going to further advance this project so it can be used in many locations, as Brian was mentioning. So we want to continue this not only for the act of getting people into the weightlifting scene, because me as a trainer and a weightlifter, it's very important to get people in that aspect because we need our help. And also we want to continue this in many other aspects. And I'll leave that over to Brian.
So my personal favorite part of this project is that we actually did 2 separate projects. One is what could we design and manufacture and present to you in 10 months, and this is the solution to that question. The other one was we didn't really end up, we didn't have the idea of creating something new, but months of research has proven to us that no one has ever done this before. We have a completely original idea. So what can CWOD become in the future? As Lily said, we can add visual receptors, we can add speech, but that's thinking small scale. Yes, we want to have it in high schools and gyms teaching you how to lift weights properly, but CWOD is a very beginning phase. You can have this in recreational therapy, in physical therapy. You can have it in hospitals, in surgery. You can have it in taking care of the elderly. The possibilities are really limitless when it comes to CWOD. As far as what's left for the three of us, we took this design from an open source called the Poppy Project, and we made our alterations to it. The way that Poppy is successful is because people give back to the open source. We always had the intention of giving back, and we do want to give our design back to the Poppy Project. And the last thing that we want to do is get a patent for this and just have our legal stamp on the idea of CWOD.
We'll open the floor for any questions. Thank you.
I have a question for you guys. So, was there a fundamental problem that you guys were trying to solve with this design? Has there been any type of study showing that there is a numerous number of injuries because people don't know how to do this? And then I have a second question for you guys as well after you answer this one.
Okay, so for the first question, I'll take it because I've been in personal training since I was 17. And not only have I asked many people around me because I've been at different gyms, I see it every day. You go to the gym and I have my own personal clients, and then I'll see everybody else in the gym just doing things wrong. They think they're doing it right. But if you look at it in a gym perspective, in which I've been also in the managing side, when you have people with injuries, let's say you have 80 people who are part of the gym, and 30 of those people have an injury due to lifting weights the improper way, not having a trainer or anybody to help assist them, or a robot like CWOD to help assist them. They're losing those 30 people within a month revenue because they'll freeze their membership, they're hurt, so on and so forth. So it's many cases of people not doing it right. It's just undocumented because those people don't have a trainer or somebody to help them. So it's like a visual study, as well as asking many trainers from different gyms.
So wouldn't that robot replace a job for somebody like you?
No, because I'm giving someone a workout scheme. I'm with my client. So let's say Brian's my client. He's a regular gym user. I'm with him. I'm giving him his workout. I'm showing him how to do it. But it's for those other people that don't have, or they don't have anybody to help them. CWOD is just correcting your form, showing you what you're doing wrong. It's not giving you a workout plan as a personal trainer would.
Yeah, like personally, I can answer that. When I go to the gym and sometimes I see the equipment and I don't know how to use it, they give you little pictures for you to follow, and sometimes it's not clear to how to use the equipment. So if you had a little robot teaching you how to do it, it'll be a little more easier for you, like actually do it right and not hurt yourself while doing the exercise.
And to add to what they said, back to your first question, there has been research done that the difference between 1 degree is the difference between a good workout maximizing your muscles and something that can put you at risk for injury. So it is a big thing. And as far as the trainers, we went extensively in our report. This is not meant to replace anybody, it's meant to help. Trainers are expensive, but there's not enough of them.
Okay. One thing that you might have mentioned and I probably missed is this robot equipped with any type of speaker audio?
It's not.
So
This is the initial prototype.
right, but I mean when I think about learning, right? Learning is visual, audio, right? So the audio component, I think it would be very important on this robot because you can look at it and see how it's doing it, but if it will be speaking, right, and actually providing instructions like, okay, you need to put your wrist at this angle, 35, 40 degrees.
So future it will have, and we have certain locations for that speaker to be there, but as one of the alterations we changed the head because we did a prototype would not have that. But for future endeavors, yes it will.
Okay. Thank you.
So in our age of technology, I can look up what the workout looks like on my phone at the gym. How does this help me versus just looking it up from a professional trainer online for free?
I mean, it's a different approach to doing it. You can look at it through your phone, but it would also be nice to have a robot and doing it for you. Some people, like for example, you go to the gym and you leave the phone in the locker. You don't want to have your phone all the time. So this might be like a better option.
Even on the phone, I can tell you from experience, I'll see people, and it's pretty funny. They'll go and they'll look at it, and then they'll do it. And they'll be doing this. This right here, that's not the proper lift for a bicep curl. Your body's moving, your body's not stationary. You should be stationary, and the robot will tell you that. Your arm should not move, it should be going up to 90 degrees and back down to 180. so on and so forth. So you can have the video all you want, but for if somebody's not giving you the technicality of the lift, you won't get it right.
So I would assume that this is your, let's say your skeleton, right? If I were to put this in a gym, let's say you have your full production upper torso, right? That we're going to use for just dumbbells and so forth. You will mask that with either some polyurethane, mask type of tissue, something that would resemble what a real human arm would look like, in order to show the good kinematic with the movement of the actual arm. Because at this point, just like that, nobody will get it.
For our final design, we had the idea of putting a skin made of carbon fiber. So that's the idea, but as far as an initial prototype, our whole philosophy was, let's simple it down, let's get something that works and can show you at least visually what you're doing.
We also looked at many places through some professors here that does the wiring around, so you can have a carbon fiber shield. So we were looking into it, but
yeah, because for example, us mechanical engineers, I can relate to it, how to move the joints and all the degrees of freedom. But for the casual exercise guru out there, they don't know how to twist it 2-3 degrees out, or right there, just by concept, you can't see it. It doesn't strike me as something I could use. Embellishing in that area, or morphing it into more human-like feature.
Which is also why in future designs we want to add visual receptors, we want to add speech. This right here, it's a great starting point, but it's not meant to teach you right now exactly how to do it. It can, but it's not meant for that.
I had 2 areas of questions. One is, did you need to use those motors?
did we need to use those?
Yes.
Yes.
I mean, they were your most expensive motors, and for the function that you've got here, with the loads that you're applying to those motors, do you really need to use that expensive a motor?
We didn't modify some of the parts, so those parts need that motor, because the other motors are...
But it's cheap to get the 3D printed part adjusted.
Right, so
You could have taken the cost out of this whole budget.
These motors we can still use for the future design. So these motors are not going to be thrown away or anything. So yes, technically we needed to use those motors because for the future design we're going to be using those exact motors.
Okay, that's the first one. Second one, if you're using this as a visual aid, I would even go a step further away from kind of what his suggestion is, and going to put protractors or something that gives me the ability from across the room to see it's truly 90 degrees or it's truly this distance. If that's the important thing to learn, if I'm going to get hurt by 1 degree, I can't tell that with that robot today.
Okay.
Does that make sense?
Any other questions?